So what's going on here? So let's think about this in a slightly more abstract way. Okay, so let's write down A, and we'll think of A as a 2-digit number just to start off with. And so A has a tens digit and it has a ones digit, right? So A1 and A0 are the 2 digits of A. So here's the tens place. Here's the tens place, and here's the ones place. All right, so A1 and A0 are 1-digit numbers. Okay, that's the picture here. So there's A. B is going to be represented the same way, B1, B0. Right, and I know this is not a common way of thinking about this, and there's going to be a temptation to read A1, A0 and think that I mean A1 times A0. That's not what I'm doing here. I'm writing A1 and A0 as the 2 digits of A. So you almost should read this like it's a string of digits, where A1 and A0 are digits. A1 and A0 here are not multiplied together. So the question is, how do I multiply A and B? So A times B equals what? Well, I know that since these are 2-digit numbers, that what I get out is going to be a 3-digit number at most, right? So what I'll get out is, and I'll call this, I'll call this C. So C2 times 10 squared plus C1 times 10 to the 1 plus C0 times 10 to the 0, right? Where now C2 is the hundreds place digit of the product, and so on. C1 is the tens place digit, and so on. And so here I can, the observation of this approach, this multiplication approach, is that I can write C2, C1, and C0 in terms of the digits of A and B in a simple way. Or I should say in a clever way, right? So C2 equals the tens digits of A and B multiplied together. So A1 times B1. And I should say A1 times B1 to be very explicit about that. So A1 times B1. C0 is the ones digits of A and B. So A0 times B0. Okay, and so that's not unexpected. But then I can write C1 in this alternative form. Right? C1 is not in the form that you would get if you just multiplied these things by brute force. Instead, C1 is written in this clever way. So A1 plus A0. So it's the 2 digits of A added together times the 2 digits of B added together. Okay, minus the sum of C2 and C0. Right? So minus C2 plus C0. And I strongly encourage you to go into the class notebook, plug this formula, or plug the numbers from our previous example into this formula, and convince yourself this is true. Right? Make sure that you believe the things I'm saying before you continue. But this is just rewriting everything I did in the previous video now in an abstract form. Okay, and so what are we doing? Well, we've got these 2-digit numbers that we're trying to multiply together. And what this shows is that I can do that with only 3 multiplications, right? Because I can save some of the work to compute C1 by using my answers for C0 and C2. Right? The hundreds place and the ones place give me some of the piece of the puzzle to answer the tens place. Okay, so that's the basic idea. Okay, so let's generalize further. Right? Let's think about how this can go even further than what we've got right here. So what I'll do is I'll say, let's suppose that our A and our B have n digits. Okay, so what if A and B are n-digit numbers? Okay. So n-digit numbers now are going to have a zeros place, a ones place, a tens place, a hundreds place, all the way up to a 10 to the power of n's place. Okay, so what this means is that I can write A. Well, so let me just before I go to the fully general example, let me just think about how to translate exactly what I just did above down into n equals 2. So suppose n is 2, right? So let n equal 2 for this example. Then what do we have? Well, we've got a equals a1 times 10 to the what? To the n over 2. Right? I'm writing this now all in terms of n. So a1 times 10 to the n over 2 plus a0. So a now is, we're thinking of a as a 2-digit number. The 2 digits take the, there's one with 10 to the half the number of digits, and 1 times 1, okay? And then so b is then b1 times 10 to the n over 2 plus b0, okay? And so then what's the product? Well, the product of the two is, I've got a times b, which I could just rewrite those two expressions that I got, but a times b simply equals a1 b1, so a1 times b1 times 10 to the n, okay, plus all this stuff, right, plus the c1 times 10 to the n over 2, plus a0, b0 times 10 to the 0. And I'll just leave that as a0, b0. And our interesting observation was that there's a clever way of writing this. Clever way to write this. Okay, but this is the picture, right? This is precisely what I just did when n equals 2. Right? When n equals 2, I'm describing multiplying two 2-digit numbers, right? And what I end up with is a 3-digit number whose largest place is 10 to the 2, right? Whose most significant digit is 10 to the 2. So let's think if we can take this concept and apply it to something a little bit more complex. Right? So let's see if we can take this concept and multiply together two 4-digit numbers. Okay, so the question is, can we multiply two 4-digit numbers using a similar technique? Right? So let's do 1, 2, 3, 4 times 5, 6, 7, 8. Okay, and let's think about a strange way of writing down these two numbers. So this is not going to be what you're used to thinking about, but it's a totally legitimate way of thinking about it. And what we're going to try to do is we're going to try to write them in this form. Okay, so now what is n? So n is 4. So let's think about how, let's call this a and we'll call this b. Let's think about what a1 and a0 would have to be to write these numbers down in this form. Okay, so n equals 4, so n over 2 equals 2. So what we're going to do is we're going to essentially write these numbers in the following way. So we're going to say 1, 2, 3, 4 should be something times 10 to the n over 2, or 10 squared, plus something. And to fill in those blanks, we just take the first 2 digits of the number and the second 2 digits of the number. So this is exactly equal to 12 times 100, right, plus 34. Okay, and so there we have it. We have it exactly in this form. Okay, and so if I want to write 5, 6, 7, 8, I can write this as 56 times 10 to the n over 2, right, 10 to the 2, plus 78. All right. Now what do I do with these? Well, I've got them in a form. I've got, a number 12 times 10 squared plus a number. I've got a number times 10 squared plus a number. And so I can actually just apply exactly this same thing and get the right answer, right? Or at least and get a step towards the right answer. In other words, what I can do is I can convert two 4-digit number multiplications into how many? 3 2-digit number multiplications. Okay, so what does that look like? Well, let's write this down. So 1, 2, 3, 4 times 5, 6, 7, 8. And following the pattern that we established earlier, what this looks like is 12 times 56. Right? So there's our C0, or sorry, there's our C, sort of like our C2. Okay, there's our C2 times 10 to the 4, times 10 to the n, plus something, so 12 times 78, plus 34 times 56, times 10 to the 2. Right, and all I'm doing is cross multiplying, right? So the 12 times 78 says I've got this times this. 56 times 34 says I've got this times this, right? And you know, each of those has one factor of 10 to the 2, so I add them together and I combine terms, and that's all fine. So then plus at the end, plus 34 times 78. Right? And our observation from before is that we can write this in a clever way that only requires one multiplication. So what's that clever way? Well, that clever way observes that if I write C2 here and I write this as C0, then I can write this middle one, C1, like this. C1 equals what? Well, it equals 12 plus 34 times 56 plus 78 minus C2 minus C0. Right? So overall, if we track how many multiplications occurred, we've got a multiplication here, a multiplication here, and then rather than do those two in the middle, we just do this additional one and then copy down our answers for C2 and C0 to compute C1. Right? So what do we have? Okay, so here's the takeaway. And, you know, this is the kind of the message in the end, is to multiply two 4-digit numbers. We can use this approach that we kind of gained intuitively from small numbers. We can use this approach to compute this multiplication by performing only 3 2-digit multiplications. So notice each of these red underlined multiplications here is a multiplication of 2-digit numbers. Okay? So to multiply two 4-digit numbers, we first multiply 3 2-digit numbers. Okay, so this looks recursive, right? This looks a little bit recursive. And it turns out that this completely generalizes. Okay, so it turns out that we can replace 4 with n, and we can replace 2 with n over 2. And so here is the concept, here's the basic root of the idea of this integer multiplication algorithm, which, by the way, is called Karatsuba's algorithm. So Karatsuba's algorithm makes the observation that is identical to what we've been working on all the way through this video, and it says to multiply two n-digit numbers, first what you have to do is multiply 3 n over 2-digit numbers. Okay, a little bit odd, right? It's odd to think about this, right? But notice that when we first began this discussion, the way we did it is we said to multiply two n-digit numbers, you have to multiply 4 n over 2-digit numbers. Okay, and we did that specifically on the example with where n equals 2, but it generalizes to anything. So Karatsuba's algorithm basically says to multiply two n-digit numbers, first multiply 3 n over 2-digit numbers. 3 n over 2-digit numbers. Okay. Right? And so this is it has a clear recursive character to it, right? It just says, you know, don't try to do the multiplication, just split the problem up and then send it down into the recursion and let the recursion handle it for you. And so what do we have? We've got a divide and conquer algorithm, right? And so what is the recurrence relation for this algorithm? Well, it says T of n, right? How many multiplications have to be performed to multiply two n-digit numbers? Well, what Karatsuba says is, well, to do this, you multiply 3 n over 2-digit numbers. So 3 times however many multiplications it takes to multiply n over 2-digit numbers. So, and then plus some kind of constant effort, right? So there's no kind of interestingness happening here in the overhead term. It's just a plus 1 to say we're splitting this thing up, right? There's some simple overhead here, and we know how to analyze this, right? This is something that we're now familiar with. And in fact, we can observe almost immediately that this is a recursion limited recurrence relation, because the overhead is tiny, right? So anytime the overhead is tiny and the recursion is relatively heavy, it's going to be recursion heavy. So we're in case 3 of the master theorem that says T of n is big theta of n to the log base 2 of 3, right? Which is approximately big theta of n to the 1.58. Okay. And so this is the basic idea of Karatsuba's integer multiplication algorithm. Now, I'm not going to go into the depths of the pseudocode. You can look this up anywhere you like. There's plenty of resources online and in the textbook, in any number of textbooks, in fact. I just wanted to give this as an example of a divide and conquer algorithm that doesn't look obvious at all at first. It doesn't look anything like the other divide and conquer algorithms we analyzed in this course, but it completely and immediately fits into the divide and conquer framework. Another one I suggest you look up, I won't go through it in a video, but another one I suggest you look up is something called Strassen's algorithm. I've already messed it up. So Strassen's algorithm, which performs something very similar. It's a very, very strange. Just a moment. OneNote decided to be a total disaster. All right, we're back. So Strassen's algorithm essentially is a very similar approach to multiplying matrices. So if I have two square matrices that I want to multiply together, the sort of by hand technique, the definition-based technique, is an n-cubed algorithm, but Strassen's algorithm can multiply them in something somewhat faster, right? Not massively faster, but it ends up being, n to the 2 point something something something, rather than n to the 3. So there's the last major divide and conquer algorithm we're gonna discuss. I wanna make sure that if anybody has any questions, you have an opportunity to speak with me about it. So we'll be continuing to talk about this in the synchronous sessions. And so until then, work on the homework and see what you can get done here.